Hello everyone, last time we talked about denial of service attacks, so we continue with operational security, and in this talk I will mention briefly firewalls and intrusion detection systems. Firewalls, intrusion detection systems, intrusion prevention systems are security checking, logging, dropping or forwarding the traffic leaving or entering a network. This is actually the job of a network administrator. Firewalls generally are placed at the end of your network actually, and because they isolate a network from the internet by allowing and dropping packets. There are three types of firewalls: traditional packet filters, stateful filters, and application gateways. So let's start with traditional packet filters. These are actually packet filtering at the gateway router. Gateway router is the connection between the internal network and the ISP. Packet filtering means deciding, dropping or passing the datagrams. The basis of decisions depends on the administrator defined rules, and these basis of the filtering depends on parameters like IP address, source or destination, protocol type, TCP, UDP, ICMP. These are in the IP datagram field, or TCP, UDP source destination port, TCP flag bits, ICMP message type, or rules for datagrams and router interfaces. So there are many choices that you can have and filter, and this way allow or disallow many packets. So let's start with some of the basic examples. The basis of administrator defined rules, policy of the organization, and this can be policy for bandwidth usage, security, user productivity, etc. Below is an example policy and rule set, and in this case this is for the network with these numbers and with web server at this IP. So if you want no outside web access, your firewall setting will be drop all outgoing packets to any IP address at port 80. So this way you prevent web access. If your policy is no incoming TCP connections except those for organization's public web server, then you drop all incoming TCP SYN packets to any IP except the port which is at this is the IP for your web server at port 80, which is the default port for web. If you want to prevent web radios from eating up the available bandwidth, you can drop all incoming UDP packets except DNS packets. If your policy is to prevent your network from being used for a Smurf denial of service attack, drop all ICMP ping packets going to a broadcast address, which is this one. Or if your policy is to prevent your network from being trace routed, drop all outgoing ICMP TTL expired traffic, which is short or time to leave, which we already mentioned in our previous lectures. Filtering policies can be based on ports and IP addresses. Example is as follows: permit telnet connections to or from host on the allowed list. This way you can just choose the IP addresses and ports. Or your policy can be based on TCP ACK bit setting to prevent external clients from connecting internal servers while letting internal clients to connect external servers. How you can do it? ACK equals to 0 is for the first segment of a TCP connection. All others are 1. So you can choose a rule like this: filter all incoming segment with ACK equals to 0. This will kill all TCP connections from outside. Each router interface has its own access control list, and here below is a gateway router access control list for this source address, and rules apply from top to bottom. So here you can see some basic settings which allow, for instance, TCP connections from the source port to destination port, flagged with any. For this case it's ACK, and these two are for UDP packets. And it is always a good idea to, after allowing the things that you need, deny remaining all. So since the rules apply from top to bottom, if the request is something other than this 4, the access control list will see this line as deny the request. Let's look at the following rules in detail. These rules allow internal users to reach the web. Rule 1, this one, any TCP packet with destination port 80 is allowed to leave the network. So this way you can reach the web. Any TCP packet with source port 80 and ACK bit set to 1 is allowed to enter the network. So this way you can receive the packets from the web. But when they are 0, this will mean that external users are trying to connect the internal server, so it will be prevented with this line because they won't have the flag bit ACK equals to 1. They will be ACK equals to 0. The remaining 2 actually for DNS packets that enter and leave the network here. The last rule blocks all the remaining traffic, which I already mentioned. Stateful packet filters are different than traditional packet filters because traditional packet filters the filtering decisions are made on each packet separately. Stateful packet filters track TCP connections. Reminder, the ACL list of the traditional packet filter, any packet with ACK equals to 1 and source port 80 is allowed, including malformed packets. Stateful packet filters track all TCP connections in a connection table. A TCP connection starts with a three-way handshake, CSEC and ACK. It ends with a FIN packet or after a timeout period. So once a three-way handshake is completed, it is included in this table, which is used by stateful packet filters. So below is a sample connection table for a stateful packet filter. 3 active connections initiated from the organization's network. So currently there are 3 connections, so they are kept in the stateful packet filter. So this way you can decide if the incoming traffic or outgoing traffic is part of these open connections. Below is an access control list for a stateful filter. Again, let's look at them. The connection table and access control list work together. Below is a sample procedure for a stateful filter. An attacker sends a malformed datagram packet with TCP source port 80 and ACK flag set. Suppose that the source port is this, 12,543, and source IP is this one. The firewall checks the ACL. The ACL says that the connection table must be checked before allowing this packet to enter the network. The firewall checks the connection table. It is not part of an ongoing TCP connection. The firewall blocks the packet. So maybe let's look at the thing in a maybe let's clarify it again. So if this is the packet received by the attacker, the firewall will allow it because it matches with this, because there is an ACK flag bit and the destination port is larger than this, so your ACL list filter allows it. But since you have stateful packet filters, you have to go back to the open connections here, and you will realize that this malformed packet is not coming from the connection that is established already. So this way your firewall will block it. So this is why stateful packet filters somewhat better than the traditional ones. Below is another example. An internet user wants to visit an external web page. The user sends a TCP SYN segment to initiate the TCP connection. The user's TCP connection is inserted to the connection table. The server responds with back packets with packets with ACK set. The firewall checks the table. A corresponding connection is in progress, so the firewall allows the packets to pass. let's move on to application gateway. Packet headers, IP, TCP, and UDP do not include data for internal user's identity. So user identity is involved in application layer data. Application gateway is an application-specific server. All inbound and outbound application data passes through an application server. Firewalls combine packet filters with application gateways. So let's have a picture again here. So this is the network. There's an application gateway here. So firewall with an application gateway and a filter. The configuration of the router's filter block all telnet connections except the ones from the application gateway. So computers here cannot use the connection, cannot create a telnet connection from here to the internet. But first they have to create a telnet session to application gateway, then the application gateway creates a telnet connection which is allowed by the firewall. So the user first sets up a telnet session with the application gateway. The application gateway sets up a telnet connection with the external host. In order to protect your privacy, you can use a proxy server because you may not want to reveal your IP address to an external host, your visited websites and traffic data to your local ISP. The solution is as follows. You can use a trusted proxy server and then use SSL communication. So idea is as follows. So Alice wants to visit a web page. Instead of visiting it with SSL communication, so in an encrypted way, Alice says the proxy server that she wants to visit this web page. So instead of Alice, your proxy visits the web page. So web page only sees the IP of the proxy. Proxy receives the data from the web page and sends back to the Alice in an encrypted way, again with SSL, so your ISP and the web page would not have information about this communication. But here the important thing is the proxy server should be a trusted proxy server. So the proxy server acts as an application gateway. The user makes an SSL connection to the proxy and sends an SSL encrypted HTTP request to the proxy. The proxy decrypts the request and forwards the clear text HTTP request to the web page. The proxy returns the response to the user in SSL. As I already mentioned, the website sees the IP of the proxy, not the user, and the ISP sees encrypted traffic from the user and the proxy. What is the challenge? As I already told you, the proxy server has to be a trusted server, because the proxy logs the user's IP address, the visited addresses, and the traffic between the user and the external host. This is important because for legal purposes, they have to keep this data, and when necessary, they have to give this data to the law enforcement. But can we really anonymize our internet activity? Tor is an example for this. It's an anonymizing and privacy service. So if you go back to picture, here we have a single proxy. What happens if we increase the number of proxies? So assume that there are 3 proxies. So you first communicate the first one, it connects to the second, it connects to the third, and then they connect to the web page. So now you make the process harder, but if all of the 3 proxies are not trusted, then your privacy is lost again. So how we can solve this problem? Tor solves this problem in the following way. So there are many proxy servers, so anybody using the system can choose to be a node. So there are many nodes in the network, and when you connect to the Tor network, you randomly choose 3 of these nodes, and this is the 3 of them will become your proxy servers actually. So Tor has a proxy pool. You can be a part of it if you want. Independent users contribute proxies to the pool. Clear text is sent from the last proxy to the server, but the proxy does not know the IP address of the user. So you might say that why we are using 3 proxies but not 1, because as you can see, if you don't trust a single one, then the system fails. And if you use 2, it is again not enough for privacy, but the least number of numbers to provide privacy is 3. So if you have like 100 proxy servers, connected to each other in this example. I mean, if you use the Tor network, but instead of using 3 nodes, if you use 100 nodes, your privacy will be even better. But using 100 proxies will mean that your internet traffic will be really slow. So this is why Tor is using 3 proxy servers to provide you this kind of privacy. So think about why 2 nodes would not be enough for you. What kind of privacy problems can be caused by using only 2? Okay. So actually Tor is still an active research area. Let's move on to intrusion detection systems. Firewalls are just packet inspection through the inspection of header fields. Deep packet inspection, the inspection of the application packets. Intrusion detection system, a device that generates alerts when it observes potentially malicious traffic. Intrusion prevention systems are devices that filters our suspicious traffic. So one of them just detects it, but the prevention system acts on these alerts. They are used for detecting attacks like port scans, denial of service attacks, worms and viruses, operating system or application vulnerability attacks, and so on. The challenge is how to detect suspicious traffic. This is a problem. So we have an example for an organizational architecture. So you have the internet, you have your filter here, firewalls. There's internal network and there's demilitarized zone. So it is divided into 2 networks. So you have IDS at the top of this network. So 2 regions of the network: high security region protected by a packet filter and an application gateway monitored by IDS sensors. Low security region, demilitarized zone, protected by a packet filter and monitored by IDS sensors. Sometimes it is a good idea to use multiple IDS sensors to distribute load. And there are 2 types of IDS systems. One of them signature based, so you have a database of attack signatures. But the other ones are anomaly based, creates a traffic profile and observes the traffic against the normal profile. So again, here you can use machine learning techniques and so on, but as I already mentioned in our previous video, anomaly detection just by using a machine learning techniques would create enormous number of false alarms, and they cannot be checked by human hands one by one. So it is always a good idea to use both of them at the same time. Because the signature-based filters would eliminate most of the false alarms so that you can check by yourself. So let's first start with signature-based IDS. The concept of attack signature, characteristics about a single packet, for example, source destination port, specific bit strings in the packet payload, and so on. Characteristics of a series of packets. Each packet is compared to the signatures in the attack database. In case of a match, an alert is generated. The disadvantages are no protection against zero-day attacks and intense traffic analysis. We have an example, Snort, which is an open source intrusion detection system, and it is widely used in this area. The sniffing interface is libpcap, also used by Wireshark. A sample Snort signature is given here, and here the parameters are explained below. Home net is the organizational network, external net is the network outside. I type here is ICMP ping packet. D size, payload size. If this happens, the alert will give the message ICMP ping mmap. So this would mean that when you have any ICMP ping packet from one side with 0 payload size, this will generate this alert. Snort has the advantages of being an open source application. In case of a novel attack, the community updates the signature database in hours. Anomaly-based IDS. The first step is to create a traffic profile and observe traffic in normal operation. Check for statistically unusual packet streams, for example, a sudden increase in port scans and so on. The advantage is no need for previous attack signature knowledge. The disadvantage is to discriminate between normal traffic and statistically unusual traffic. This is a recent research topic because I already mentioned a lot, but here it is hard to create a traffic profile that will be considered as normal, because a lot of users will behave differently in time, so all of them will appear as an anomaly. So this is why I always encourage people to use signature-based together with anomaly-based IDS.